the posted PowerPoints that you can see on the Canvas shell, and I'm gonna embed my notes in between. Okay, then, because I need maybe sometimes to share some of the I will say figures or some of the other let's say tables and all the stuff. Okay, today mainly we are going to talk about physics and what is physics as a science and how it is related to nature. We are going to introduce units and the system of units that we are going to use. We are going to introduce something called dimensional analysis that is gonna help us in maybe like sometimes identifying any mistake in our formulas, or we can use it actually in I will say the other thing that we can use it is for deriving units. We will talk about significant figures, also how to convert units, and kind of order of magnitude calculations. The order of magnitude calculations can give us a common sense method of judging our answers. We're going to talk briefly about scalars and vectors because this is a key point in identifying quantities in physics and how we are going to deal with them, and what really are the methods for problem solving, or like the techniques that we are going to, like maybe day by day, we are going to introduce throughout the course. Okay, now the first thing is what is physics. Okay, and I will say like most of scientists, they will agree that physics, it is the study of nature. I want to make this here. All right. Okay, then I will say physics is the study of the fundamental laws of nature. And you are going to see that we will, for example, study in Newton's first law, and then in Newton's second law, for example, I'm giving you just, and in Newton's third law, and all of them, they're gonna talk about motion, and that motion in general, I will say, we are going to move to anything that is in motion and describe the motion and know something about how this motion was initiated. And also we can go very complex. We can go maybe to black holes or a study of the universe and trying to find what are really the things that are really around us, how they're gonna work, how they're gonna rotate, how they're gonna interact, all these. We are going to introduce, of course, concepts of like very important quantities, energy, momentum, and every time I will talk about, a quantity, these I am calling them physical quantities. Now, what are really the physical quantities? I will say a physical quantity, it is a quantity that can be measured or calculated. And just to show you how the lecture and lab are really related, most of the time I will talk about that connection. For example, in the lab, you will collect some points or like some measurements. We call them data or data. Okay, now that is going to be a number plus a unit. And here, just because always I find my students confused about it, I will say any quantity that you measure or it was given to you, because some of the labs, remember, are virtual, completely virtual, then these are that you are going to have them under the data, and I will say usually we have the data tabulated in a table. Okay, just this is as I said, connection to what we have in the lab. Now examples on these quantities: distance, weight, mass, time, velocity, acceleration, speed, and we have so many of these. Then these are some of the quantities that we are going to study. And as I said, some of them, they're gonna be, I will say, like measured, then they're gonna show under data, and some of them, they will be calculated then in your lab under calculations. Okay, let's say assume here you have measured mass, and this was in kilograms, and let's say 10, 20, 30, whatever. Then here you might have also another weight. Let's say I want to calculate the weight, then I might have like another table called like the weight, and this is in newtons, and then I will calculate. I need to show also a sample calculation. Then this is just to show you like all these like physical quantities. I mentioned here that every data point is going to have a number and a unit, and just the unit here we are using kind of units that they're going to be maybe different in different systems. What we're going to do today is we are going to unify our systems for unit, and we are going to use just one system. Now, I will say like some of the questions or some of the things that we are going to deal with, we call them qualitative. Qualitative means I will not use numbers, but I will say maybe, okay, this mass is bigger than this mass, or this velocity is, let's say, greater than this one, or, just you're going to compare qualitatively. Now, in physics, most of the time, we need to make quantitative comparisons, then we need to measure. Then, like, quantitative means you are going to have numbers. And for any measurement, we should have a particular standard that is going to use, we call it unit. Now, for, let's say, length, we might use units of inches, as we are using here in the United States, or miles. We can use meters, we can use kilometers, okay? But the thing is, I will say, we need to have a standard that we are going to all agree on, and that was made actually in France long time ago. They have created a system that everybody in, I would say, the world is going to use it. Like the system, because it's French, it's called Système International, and that is SI system. We can call it sometimes the international system of units. We some of the people, they call it the metric. They have like many names for it, but the thing that I will say, it is more convenient to use one system throughout all the countries, because this is going to make it for us easy on comparing results from one place to another. Now, in that system, we did use 3 basic quantities. Then we decided we are going to have 3 basic, I would say we have more, of course, but for this course, we are going to talk only about the three basic quantities. And the first one, it is length. The second one, it is mass. And the third one is time. Okay, and the length, I will say we use the meter, and it was measured as 1/10,000,000th of the distance from the North Pole to the equator. Actually, it's not only that, it was really, there was a history of changing these. Now, it is measured by the distance traveled by light in a vacuum in 1/, this is speed of light of a second. Then this is like the new definition for the length. And when we will say the meter, this is the new definition of the unit used for length, which is meters. And just here I'm telling you like how big the unit is, okay, so that you have the, I will say, the feeling of the 1 meter. Okay, now also for the mass we did use kilograms, and here I want to bring to your attention that we are using lowercase m, okay, for meter, and we are using here lowercase k and lowercase g for kilogram. Now 1 kilogram, it is just the mass of, I will say, an alloy that they are made of platinum and iridium, and these are really two metals that they're gonna resist any changes from the environment. And it is kept at the International Bureau of Weights and Standards in this is the city Sèvres in France. Now the time, it is measured in seconds, and again it is lowercase s, and it's gonna be the second, that is the time for radiation from cesium, one type of cesium atoms. It is one of the isotopes 133 to complete this number of oscillations or cycles. Okay, now also I will say, although we are going to use mainly these three, but there are more basic units, and these are the ones that they're gonna be like the ABC of the physics or the ABC of the units. And then after that we are going to use I will say any unit is going to be derived from these units. Now of course here the meter, okay, the meter here, I don't know why it's wrong. Okay, it's m, it is length unit, kilogram, kg, mass, second, s, time. Now ampere, of course, we will not study any electricity in this course. It is capital A. For the temperature, we're going to study, it is Kelvin, K, uppercase. Luminous intensity, this is for light, and we will not study anything related to this topic. Candela, CD, and amount of substance, small, we will talk about it a little bit. Now, here we are showing you that we have so many, things of different sizes that we might also encounter in this course and or other courses, and showing you some of the typical distances. Like inside the nucleus, we have protons, and the diameter of proton is 10 to minus 15 meter. And we have like all these like lengths up till we have the distance from the Earth to the nearest large galaxy, which is the Andromeda. It is 2 to 22 meters. Then it's just a range of lengths that we might encounter along. Now also here, some of the typical masses, like the galaxy, 410 to 41, and the electron is 9.11, 10 to minus 31. Okay, the lightest, maybe among all the things that we have in here. Also for time, we have like different times here showing you that the age of the universe is 510 to 17 seconds, whereas one cycle of a visible light wave is gonna last for 10 to minus 15 seconds. And if you noticed here that the numbers are getting really very big and very small, and this is the reason why I will say first, just before going into the prefixes, I want to go over what is called the scientific method, the scientific notation. Okay, there is, I will say, a notation that we call it a standard notation. And that standard notation means that you are going to, let's say, mass of the electron. Mass of the electron, it was recorded here as 9.11. 10 to minus 31 kilograms. I will say mass of the electron in this is in the scientific notation. Okay, in the standard notation, we can write it like this. Even I don't know if I did a mistake or not. Okay, this is okay, and you can see it's not convenient at all. I might make a mistake. I might have you know, like just more space, more ink, more whatever. Like it's not convenient, and this is the reason why I have converted to this neat notation, which is called the scientific notation. And maybe something that I want you to think of, it is like I can write this number as this, and I want you to find out if this is also a valid scientific notation. Why? Why not? Okay. Also, in order to overcome these difficulties, I will say, and okay, this is not the only like reason I will say we are using the scientific notation. You're going to see in your first lab, you are going to do some of the calculation. Then it's easier for you whenever you are going to make like multiplication or division or anything, that when you have the numbers in scientific notation, they are going to be easy to handle. Also, I have here for you some of what is called common prefixes, which is, let's say, I will go over the ones that we are mostly using, like the giga, which is uppercase G, and it is 10 to 9. The mega, everybody's familiar. The kilo as well. Okay, and also I will say the centi, the milli, these are like micro. If we will go to electricity, we will be maybe dealing more with nano, pico, femto, but not femto, femto when we go to nucleus. But I mean, these are really some of the common prefixes that we are going to use it, and they are really convenient, making the numbers like neater. Then when you're gonna say, let's say there is a I will say there is a turtle that is moving, instead of saying, let's say 0.000 like 0.003, let's say meters in 1 second, maybe I will say like 3 millimeters. Then it's like more convenient. Now here, just to show you that the diameter of a red blood cell is approximately 7 micrometers, which is really the thing that is going to make it like more convenient. And then you need to know that it is in meters is going to be 7 × 10⁻⁶ and in kilometers is going to be 10⁻⁹. Here what I use actually for this easy conversion, I usually teach my students kind of a neat method for converting, which is because these you need to know, like these conversion factors you will not get. Like this is if I have 1 kilo here, it's not only for length, but I'm using it widely for length. And then this is the 1 meter is going to be here. I have the decimeter here, centimeter here, millimeter here. Then if you will convert downwards, you're going to multiply times 10 for every step. And if you are going to go up, is going to be divided by 10 for every step. And for example, like I can say 1 kilometer is, okay, 1, 2, 3 steps, then it's going to be 10 times 10 times 10, which is going to be 1,000 meters. Okay, then it's really good to know how to convert. Okay, now I will find out something about what is called dimensional analysis. Now, the dimension is going to tell you what is the type of the quantity. Is it length? Is it mass? Is it whatever? Like, okay, then a distance, I will say it's a dimension, whether it is measured in feet or light years. A distance is a dimension regardless what the units are used. And also time is another dimension. Okay, and for the dimensional analysis we are using for distance, we call this like usually the dimension of length. Okay, and then area is going to be L squared, volume L cubed. We can derive, okay, and as I said, we are using this in deriving units or verifying if my quantities, my equations are really correct. For example, here, I'm showing you that this is the equation x equals x0 plus vt, and we know this is a dimension of length, and this is dimension of length, and this one is dimension of length over dimension of time, then, and this is time, then you will find that this is gonna cancel, which means length equals length plus length, which is consistent. Okay, for example, if I forgot the t, then I will say it is L equals L plus L over t, and that is not going to make it correct. Okay, then this is really not consistent, and then I will say I will reject this equation. Then these are the two reasons that we are using for measuring, like I will say, implementing dimensional analysis for. Okay, then here, this is another equation, and also showing that it is also consistent. Okay, now for significant figures, why we use significant figures first, and like in the lab you're going to find most of the time I'm gonna ask about like the rubric. I'm gonna say, oh, there you should have your number of figures consistent. Okay, why we are using these? Because all measurements are really approximations. We cannot have an exact measurement, okay? And then we're using the significant figures to tell what is the number of digits in a quantity that are known with a certain certainty. Okay, then there is a limitation that is going to be brought for us by different tools, using different tools, and I will say we are going to use the rules for significant figures to find out what are really the like how many digits you're going to keep in the number. Now, I will say the first rule, all non-zero digits are significant. Then if you have number 1, number 2, 3, 4, 5, whatever, like numbers, they will be significant. Then I will say if I have 0.325 millimeters, this is going to be 3 sig fig. Okay? Now the zeros, they are 3 categories. Okay, when they are between two significant figures, they are significant. Then, for example, here, 0.3004 millimeters, let's say, this is for significant figures. Now, zeros at the beginning of a number are never significant, which means the ones that they are to the left. Then if you have a number 0.00035, let's say meters, this is like 2 sig fig. Now the zeros at the end of the number, or like to the right, they are really significant. Okay, then if you have a number that is going to be 0.0040700, then this one is going to be, like all these are significant, then it's going to be like 5 sig fig. Okay, because the zeros at the right are really significant. Now we have like, okay, this is how we're gonna record our measurements, or let's say decide how many significant figures I have in a number. Now we are going to move to having operations. For example, I want to add or I want to subtract. Then I want to know how many significant figures I should leave. For example, here I have rules for operations. The first one, it is about addition and subtraction. Always the general rule is saying that the accuracy of a calculated result, it is limited by the least accurate measurement involved in the calculation. And because addition and subtraction, we are going to keep the smallest number of decimals. Okay, then it is not it's not the smallest number of significant figures, it is decimals, because any number with less decimals is going to be more accurate than the one that is going to be okay, then I will say we are going to keep the smallest. For example, here showing you addition, then I have this number, it has like, I will judge through the decimals. 3 here, this one is 3 decimals, and this one is 1. Then I should keep what? I should keep 1 only. Then you are going to add, and then you are going to round. The rounding, because this one is 5 or more, is going to be 84.7. For subtraction, again, it's the same rule, because I will say subtraction and addition, they are going to be the same. Okay, then again, you're going to subtract, and then here is going to be the smallest number of decimals is 4. Then I'm going to keep my numbers to 4 decimals, not 4 significant figures. Now with multiplication and addition, multiplication and division, we keep the smallest number of significant figures. Okay, then here you are multiplying 4.36 times this number. You're gonna finally keep only two significant figures. Here, just one of the examples that we have. The turtle is traveling at 2.51 centimeters per second for 12.3 seconds. How far does the turtle go? And then you need to calculate the distance, and distance, this is assuming it is moving with constant velocity. It is velocity times time. Then you're gonna multiply 2.51 centimeters per second times 12.23 seconds. This one is 3 and this one is 4. Then I should keep only a 3 because the rule is for multiplication it's three significant figures. Again, this is the scientific notation again, and I mentioned this before, but just because I thought that maybe a better position maybe to talk about it, but just of course making big numbers look smaller and removing ambiguity with significant figures. Sometimes it's very easy for you to make it like to keep the significant figures neat, and sometimes you need to do that. Okay, for example, here makes the number of significant figures much clearer. If you have 2,500, this is not agreed on how many significant figures. Is it 2 or 3 or 4? We don't know. Ambiguous. Then if we would write this in 2.5, 10 to 3, this is not 1 or 3, then obviously this is two significant figures. If we will have a 2.50, then we know that this is gonna be 3 sig fig. Now for this one here, it is again, I will say the same idea. It is 3.6, 10 to minus 5, and that is gonna make it like 2 sig fig. Now, rounding off, miscalculation that results from rounding off numbers to a convenient number of decimals. This is because I will say rounding at every step is going to cause error. Then do the entire problem and then round the answer to get the correct number of significant figures. And usually it's easier for you to keep the numbers on your calculator and finish the calculation. And finally, at the final step, you are going to find out what is going to be the number of sig fig. Now, there are instances where we need to convert units. And for converting, I am using this method, which I believe it's very straightforward, but you can use your own method. This one is minimizing the, I would say, the mistakes. For example, here, 1 foot is 12 inches, and I want to convert 24 inches. I will create from this one here, I will create a factor that equals 1, which is going to be 1 foot divided by 12 inches, all right? And that is going to make the inches cancel, and then I will get it like 2 feet. I can also do the conversion into meters from miles into meters. One thing that I want you to know here, that usually, and maybe this is something that I want to tell you, like it's not clear here. Usually the conversion factors and some of the constants in the equations, we call them exact numbers. That means they will not affect your sig fig. Okay, I will say, okay, I don't agree with what's written in here. Then I will say, if I will do this one here, and I have, let's say, two, this is like only one. Okay, this is hard when it is only 1, 2. Then I will say, let's have 2.58 miles. And then I will use, I like to use that one. I will not use all these like digits, meters, 1 mile. Then when I will multiply this here, when I will multiply this, I will say is going to be 2.58 times 1609. And that is going to be 4151.22, okay, meters. Okay, yes. Okay, and I will say, I will not consider this in my calculation. I will talk about this one is 3 sig fig. Then I'm going to keep only here 3 sig fig, which means this is going to be 11415. Okay, just 1 second. Okay, without a decimal, I will consider this as 3 sig fig, or I can make this as significant figure thing if I want to have it clearer. Okay, then this is like this is the best. Okay, there is a one opinion that is saying that this number, if I don't have a decimal, I can consider 3 significant figures, but not all of the people are agreeing on that. Okay. Okay, for example, here, how old are you in seconds? Like you can do that calculation. Now, order of magnitude calculation, it is, so most of the time we can estimate, okay? If your estimate, your bowling ball is going 17 meters, miles per hour at impact, and your calculation says it is 4 times the speed of light, something went wrong. Okay, then it's just as I said, you are using this to judge judge like the common sense of your answer. Then I will say the order magnitude estimates are good within a factor of 10, which means is like I don't want to have like exactly the same answer, but I will say I will get that estimate that is going to make it, let's say, oh, this is like maybe 10 meters, okay, or approximately maybe, like if, and the actual number is maybe 13, okay? No choice when a precise calculation cannot be done a lot in astrophysics, and if we get within an order of magnitude, we did well. Okay, then it's just, I will say this is about the order of magnitude. Now, coordinate systems are really used to determine the exact position, your position. And this is like, this is the GPS thing, right? Now, there are two types of coordinates that we might use. The first one called Cartesian, the one that we are using always, the x and y and z. And we have the polar. The polar is going to give you how far you are from the origin with a vector called r and theta. This is polar and this is Cartesian. And there is a relation between the two. Okay, like I can relate them by saying here that x, it is r cosine theta, and y, it is r sine theta. And this is, I will say, that is going to be used very frequent in this course since we are going to deal with vectors, but I will go over it later more in details. Just a reminder with trigonometry, because this is, as I said, we are going to use it. Okay, the sine is going to be always the opposite divided by the hypotenuse. The cosine is going to be the adjacent divided by the hypotenuse, and the tan is going to be the opposite divided by the adjacent. And the cotan, we will not maybe use it that frequent, but it is something that you know. If you have a plane polar coordinate 2.535, what is the same point in the Cartesian coordinate, the one that I was talking to you? The x component is going to be 2.5 times cosine, and the y is going to be the 2.5 times sine. Also, we need also in this course Pythagorean theorem, a squared equals b squared plus c squared, and the quadratic formula to solve when we have a quadratic formula. Now, all the quantities in this course, they will be classified into scalars, either scalars or vectors. Now, the scalars are physical quantities that they have only magnitudes and units, whereas the vectors, in addition to that, they have a direction. Then a scalar, it's a numerical value, maybe positive or negative. Okay, like temperature, speed, height. Okay, and I will say always, I don't like the thing that they are saying that it might be positive or negative. I will erase that because always I'm gonna get like the magnitude. Okay, here they are talking about temperatures, and I don't want you to be confused by the negative because we are going to use the negative for the direction. Then just for now, forget about temperature because we are not dealing with temperature in the beginning, at the beginning. Vector, it's a quantity that can be having magnitude and direction, and we are using vectors like displacement, force, magnetic fields, and we represent vectors by having an arrow, which is a segment plus a head that is going to point in the direction. Okay? Okay, we will talk more about vectors later, okay? But just here, this is heads up. Now, this is this problem-solving technique. Usually is going to be, of course, you're going to read the problem carefully and finish, I will say always, finish reading the problem. Draw it and imagine it, because this is the difficulty in physics, is the connection between life and between what we have in the text, like in I will say that the problem itself is going to be very abstract for you. When you draw it or when you imagine it, you're going to have more realistic. Choose a coordinate system and visualize that physical process so that you will be able to make connections. You're going to identify knowns and unknowns and trying to find what you are looking for, because you need to identify which equation you are going to use. You are going to plug in your numbers and solve, and then most of the time you're going to check your answer using dimensional analysis for units, like, is it making sense? And maybe sometimes you need to comment on your answers. This is the summary of chapter 1. Physics is based on a small number of laws and principles. Units of length are not meters, units of mass are kilograms, and units of time are seconds. All terms in the equation must have the same dimension, okay, because we cannot add bananas plus oranges. The result of a calculation should have only as many significant figures as the least accurate measurement used in it. Convert one unit to another by multiplying by their ratio. Order of magnitude calculations are designed to be accurate within a power of 10. Scalars are numbers. Vectors have both magnitude and direction. And for the problem solving, read, draw, visualize, strategize, identify equations, solve, check, explore.